Now, if I want to do the same thing with polar coordinates, rather than taking a triangular approach of an x and a y in order to reach my destination, I first take a theta value, which is a degree measure from a certain point, that's my theta, and then an r measure, which is a distance from the origin traveling at that angle to reach a point. Now, what's different about this is that we can work from any point and it's efficient to directly get to that point. So in terms of navigation, it makes more sense to give something in terms of a polar coordinate rather than a Cartesian coordinate, because if you want to get from point A to point B, you're not going to walk 5 feet to your right and 10 feet, turn left and then walk 10 feet. That's not efficient. Instead, the same way that a Boy Scout, say, works with his compass, is you take a heading and a theta and then a distance, and you travel that. Now, let's try something a little more complicated. Say that I want to graph something, and rather than it being a simple kind of polar coordinate in which, say, our value is 5 units and our theta is 15 degrees, we want to do something a little more complicated, like it's 5 units and it's negative. Now, if it's the same 18-degree measure, the way we graph that is we still measure 15 degrees from the positive x-axis. That's our 15-degree measure. But rather than traveling in this direction, we're instead going to travel, because it's negative, we're going to mirror. So it's 15 degrees from this axis. And we're traveling 1, 2, 3, 4, 5 units in this direction. Now, let's try something where we have to convert from a Cartesian coordinate to a polar coordinate. So for example, say I have the coordinate 3, 4. And that's my point. And if we were to graph that, we would travel 3 units this way and 4 units that way to get our point. And we want to convert that to Cartesian coordinates. Well, we already know SOHCAHTOA. And we know that when we're working the Cartesian plane, we're working with 90-degree triangles. So if I were to look at this triangle, I have a 90-degree angle with a value of 4 and 3. And this is the theta we need to know to convert this. And this is our r. So we can find r simple enough. We simply take 3 squared plus 4 squared is equal to r squared. That's the Pythagorean theorem, and we're very familiar with that. So we have 9 plus 16 is equal to 25. R is equal to plus or minus 5. And we know it's going to be a plus 5 because if our radius was negative, it would put us in the third quadrant. So we know that rules out it's positive 5 is our r value. Now to find our theta, we know all 3 angles. But if we didn't know the r yet, or if the r was a decimal number that we didn't like, that wasn't pleasant to work with, we do know our x and y values, which are also our opposite and adjacent angles. So we can look at TOA from SOHCAHTOA and see that the opposite over the adjacent will be 4 over 3. So to find our theta, it is equal to 4 over 3. Or we can also say tan, so negative 1 of 4/3 is equal to theta. And let's say we'll be working in degrees. So we take out our calculator, and we go to tan the negative 1, 4 divided by 3, and we get 53.13 degrees. So theta is equal to 53.13 degrees. So now we can write our Cartesian, so now we can write our polar coordinates in order to reach the same point. Would be our r value of 5 and our theta of 53.13 degrees. Now, if we want to just graph directly from that, it's slightly difficult to do with a Cartesian coordinate plane because we have to work in finding our angle with a protractor or something, and then finding what 5 units along that would be, which we'd inevitably need to convert to Cartesian coordinates, which is why polar coordinate graph paper comes in handy. Now, polar coordinate graph paper is laid out differently than Cartesian graph paper. Polar coordinate graph paper still has the xy axis, but instead of horizontal and vertical lines, it has a system of spheres, or circles, that continue, oh dear, out from the center. And we'd use our r value of, say, 5 to travel this distance. And then it also has sublines of degree or radian measure that assist us in finding the degree we'd want to graph. So, this is a simple explanation of polar coordinates, which in theory is very easy. It's simply, instead of traveling linear directions to reach a point, we're traveling an angle and then a distance, a radius of sorts.